Resistance is a measure of the degree that an object opposes the movement of electric charge. So for example, if we attach some element to this circuit made of a certain material and close this circuit, then if this material was copper, then that's a conductor that easily allows electrons to flow through it. But if the material was glass fiber, then the current would be too small to measure. Because as we know, with a conductor, such as copper, the valence electrons are free to move around, whereas with an insulator, such as glass, the covalently bonded network solid won't allow electrons to flow through it. Now if we consider a resistor, which is a typical circuit element to stop the flow of current, and suppose it has a uniform geometry, so a constant cross-sectional area and a constant length, which will denote L, and the material that the resistor is made from also has a certain resistivity, which we denote ρ. So the resistance of this resistor is the resistivity multiplied by the length of the resistor on the cross-sectional area. So as you can imagine, higher resistivity, such as where we have an insulator, would result in a higher resistance. And if the resistor were longer, so there's a longer path for the charge to flow through it, so that would also increase the resistance. But a higher cross-sectional area would reduce the resistance, because as you can imagine, the charge will have a higher area to flow through, and is thereby less likely to bump into electrons that repel it. So effectively the resistance is proportional to the length of the resistor and inversely proportional to the cross-sectional area. So as an example, the resistivity of copper is 1.7 by 10 to the minus 8, and that's in units of ohm meters. So note that the resistance is in ohms, and suppose the length is in meters, and the cross-sectional area would be in meters squared. So ohm meter per meter gives the resistance in ohms. And the resistivity of glass fiber is of the order of 10 to the 12 ohm meters. So you can see it's much higher than that of copper. So effectively, the resistivity of a material is a fundamental property of the material, which as we saw, depends on the atomic and molecular structure, and quantifies how strongly the material opposes the motion of electric charge. And here we've depicted the motion of charge using conventional current. And note that the resistivity of a conductor increases with temperature. So for example, looking at the conductor, if you have a higher temperature, then the electrons would have a higher kinetic energy, then they're more likely to bump into charge that's flowing through this conductor. Now suppose we have a resistor with uniform geometry, so it has a constant cross-sectional area and length, but the resistivity varies along the length. So it's a function of L. So therefore, if we take some element that has a differential length dl, Then using this formula for the resistance, the differential resistance is the resistivity as a function of L multiplied by dl on the cross-sectional area of the resistor. So that will be this area over here, which is constant. And therefore, if we integrate both sides, we obtain a total resistance of the resistor with uniform geometry. Ohm's law relates the current, resistance, and potential difference across a conductive element of a circuit. So note that Ohm's law is not a universal law, so not all circuit materials follow it. So it basically says that the current is proportional to the voltage across the element, or potential difference, and inversely proportional to the resistance. So the higher the resistance, the lower the current through the circuit element, and the higher the voltage, being the potential difference across the circuit element, then the higher the current. Now, materials that obey Ohm's law have a constant resistance for all currents and are called ohmic materials. So in other words, the ratio of the voltage to the current is a constant. And an example of a non-ohmic material is a light bulb. So this doesn't obey Ohm's law. And an ohmic material has a constant resistivity. So recall, if the resistance is constant for a uniform material, then the resistivity must also be constant. And the resistivity is constant regardless of temperature. So note that resistors can convert electrical energy into thermal energy, and that may change the temperature of both the resistor and its environment. So as you can imagine, when the resistor dissipates electrical energy, it gets hot. So for an ohmic material, we can plot the current versus the voltage, and the slope of the current to the voltage is the reciprocal of the resistance, which is constant. So therefore, the resistance of an ohmic circuit element can be determined from the slope of the graph of the current in the element as a function of the potential difference across the element. A cylindrical wire has a radius of 2 millimeters and a length of 1 meter. And it has a resistivity of 2 by 10 to the minus 8 ohm meters. Now, if each end of the wire is attached to a 12-volt power supply, find the current. So recall, by Ohm's law, the current is the voltage or change in electric potential across the element on the resistance. And the resistance is the resistivity, which is 2 by 10 to the minus 8 ohm meters, multiplied by the length of the wire, which is 1 meter, on the cross-sectional area, which is pi by 2 to the minus 3 meters squared. So we have consistent units. So the resistance is 1.592 by 10 to the minus 3 ohms. So if we substitute 12 volts and the resistance, we get the current, which is 7,539.8 amps, which is quite high. Now if the wire had a resistivity that varies according to the resistivity by L, so therefore the resistivity is a function of the length along the wire. Find an expression for the resistance in terms of the resistivity, the radius and the length of the wire. So the total resistance is the integral of the resistivity as a function of L over the cross-sectional area of the wire integrated over L. So if we take a differential element along the length of this cylinder, which has a constant cross-sectional area and a differential length, then this element has a differential resistance dr. Then if we sum up these differential resistances across the length of the cylinder, then we get the total resistance. So therefore substituting for the resistivity as a function of L, we have rho being a constant by L, and then if we take the constants outside the integral, being rho on A, and integrating this expression, we get rho on A by L squared on 2, evaluated from 0 to L. And therefore the resistance would be the resistivity by the length squared on 2 by the cross-sectional area. And the cross-sectional area of this cylinder is pi by the radius squared. So as you can imagine, for a longer wire, the total resistance is higher, and for a higher radius of the cylinder, the total resistance would be lower.